All right, so Patrick has designed the study, and now all we need to do is execute it. And we're going to do that in R. And the reason why is we actually wrote a R package, or actually a set of R packages that does that for you, or helps you do that. So to find the package, you can go to our GitHub repository, and it's conveniently called CohortMethod. And what you'll find in that repository is installation instructions. So if you want to install it on your own computer, you can. Also, it might be important to point out that there is a package manual. So basically what the package is a large collection of R functions. And I'm not going to discuss all of those R functions here, because that would definitely put all of you to sleep and will make us miss lunch. And there are also things called vignettes, which in R speak, that means that there are not just reference manuals that show you all of the functions. It shows you how to use them. So I would definitely recommend going through those vignettes as well to better learn how the package works. So what I'm going to do is I'm going to show you how you can use this CohortMethod package to execute the study that Patrick has now designed. And actually, he showed you that Atlas spits out our code that calls this CohortMethod package. So that code is here. So I hope you can all read it. But I need to make a disclaimer that I'm not actually, in this morning session, going to go over the code that is currently being created by Atlas, because it actually has changed over the past year. We've added an extra layer of abstraction that allows you to do many analyses in one go. But I figured it probably is easier to first show what it looks like without the layer of abstraction, and then this afternoon I will show you what the layer of abstraction is about that will allow us to scale it up. So just so you know, the code that comes out of Atlas no longer looks like the code that I'm going to show you, but you'll see why that is in the afternoon session. All right, so the way that the package is designed is you basically get 5 steps that you need to take to go from the data in the common data model somewhere sitting on a server all the way to your estimates of the hazard ratio or odds ratio, or whatever you wanted, and all of the diagnostics. So step 1 is to talk to the database and get all of the data that you need out of the database and into R. And so what is the data that we need? Well, first of all, we need our T, our C, and our O. And basically what we need for those cohorts is the index date and the end of cohort eligibility. For example, in this study, the end of exposure. And we need to know the end of observation for people, because they either go to the end of exposure or they might be censored at the end of observation. We need to have the outcomes of interest, basically when did the dates occur. And we need to get covariates. So the T's and the C's and the O's, you can actually generate them in Atlas. So there's no magic there. We just let Atlas generate those cohorts, make sure that it picks all of those people and selects their index date. And we're going to just blindly use them in the package. There's no magic there. But we also need to get covariates. And Patrick already showed you that he'd selected covariates that he was going to use in the study. That's because Graham used several covariates, demographics, medical history, a CHAT score, HAS-BLAT score, medication use, and he handpicked those covariates for this particular study. So that's what we're also going to be doing here. So the first thing that we need is did you actually show this, Patrick, where we showed the selection of the concept IDs that he had?
I skipped over it.
All right. So this is not normally the way that we work. We normally just use all covariates, but in order to reproduce what Graham did, you'll need to basically have a list of all the concepts that he used to create covariates. So we need to load those into a R vector. And then we need to call a function called createCovariateSettings that tells the package which covariates to construct. And this is actually the bit that is not part of CohortMethod package itself, but is part of this feature extraction package that Patrick already alluded to. feature extraction itself has a package manual and vignettes to help you make some sense out of what are all these options, but I think most of them are pretty obvious. Do you want to create demographics for gender? Do you want to create demographics for race? Do you want to create demographic or covariates for age, for the Charleston Comorbidity Index? And you can just turn them on or off by setting this to true or false if you want. Here we're just setting a few of them to true, and then we say only include covariates belonging to these concepts that we defined earlier. So we really are restricting the covariates that are being constructed to a small subset just because we want to do what Graham also did. And later on, I'll actually show you how to do it the way that we normally do it, which is use everything. So now we have an object called covariate settings that instructs the package on how to construct covariates for our T and our C, baseline covariates. So when we have all of that ready, we can call this function called getDB CohortMethod data, which takes this first step, getting all of the data from the server. So of course we need to provide some connection details, and in the manual you can see how to specify that will tell you where do you find this server, which could be a SQL server or Oracle database or whatever database. We need to specify where the common data model data lives. And then we need to provide the numbers that identify the cohorts in Atlas. And so in Atlas, you will see in the URL, it will tell you what the exact ID is of the cohort that you're working on. And so Patrick generated these, or created these 3 cohort definitions. So we just reference those, and they'll be in the cohort table. So we need to specify that. And then here, we specify what the covariates are that we want to be constructed. And then that's it. You just hit go. Yep, go ahead.
So I just have a quick, could you use this package outside of Atlas?
Yes, you don't. Well, the only problem then is how are you going to get those cohorts?
Right, exactly. That's what I'm not. So this is under the assumption that you're going to be generating those cohorts in Atlas, right?
Oh, so if somebody else creates it and sends you the JSON, or I guess that would be using Atlas, sends you the SQL, could you run the SQL and it would do the same thing?
Yeah, so what we do when we run a network study is we decouple it from Atlas. So we take what Atlas generates, is the SQL, we just put that into a study package. And then whenever one runs this study package, the first thing it does, takes the SQL, creates the cohorts on the server, and then this actually points to those cohorts that you just generated. And that's also the reason why we're actually allowing you to specify different tables where these cohorts might live, because you don't want to maybe mess with what's in your local common data model version. If somebody executes a study, you may want to have a separate study table specifically for the cohorts for that study, and just create them on the fly, do your study, and then just throw the table away or something like that.
You can populate on a cohort table with whatever mechanism that you might have and utilize extraction here.
Yeah, so in theory, you don't even need to use Atlas to define the cohorts. You could just write some SQL if you're good at SQL and don't like Atlas or something, but it's usually more convenient to use Atlas to design the cohort. I mean, that's what we always do.
But specifically, the input is just a cohort object following the specification of the cohort table. So it's a cohort definition ID, a subject ID, and a cohort start date and a cohort end date. As long as that table structure is populated, you're good to go.
Could you say a little bit more about what you just said about using a separate table to keep study data that's not? You said something about the potential for interference with your local CDM instance and the use of a separate table to do something that I just want.
Okay, so imagine that you have Atlas running locally or in your institute, and you have a database according to the common data model, and Atlas is generating, when you hit the generate button in Atlas, generate cohort, it is generating cohorts in a table named cohort inside of that database. And so that will get number 1, 2, 3, 4, 5, et cetera. And then imagine somebody else comes along and says, oh, I'll execute this study, and I'll instantiate these cohorts in side of this cohort table. Well, what if I accidentally picked a cohort ID that is already in your table? And you might actually overwrite somebody else's cohort and cause all sorts of bad.
Overriding cohort defined in a different study. So
yeah, so I tend to just, like I just said, I usually not even in the same schema, but in a completely different schema. I create a table that has the same structure as the cohort table. I create all of my cohorts that I need for my study in there. I perform my study, and then afterwards I may throw away the table altogether. Because I have the information that I need to exactly replicate that table if I need to.
thanks.
So executing this one function might actually take a while, depending on how big your database is, how big your cohorts are, and how fast your hardware is. So it could be, if you specify a large number of covariates to be created for a large number of people, that it actually takes 6 hours or something. But I mean, that should be OK, right? It's just a computer working. You can go and do something else in the meantime. Yeah, get lunch, for example.
So quick question. Sorry, I think I'm a little bit hung up on that last point. So if I was at an institution and we had a constantly see nightly updated OMOP from our EHR, and you ran your study, you got your cohort, and you wanted to basically save that cohort set, is that when you would have to, as you mentioned, create your own study table and replicate the data? Because if you rerun the same cohort definition the next night, you might get a different set.
Oh, wow, yeah, we don't usually have that. Usually our CDM databases are static, but if that is the situation.
Well, just save the R object.
Well, so you can do two things. Either you create a separate table and just at a certain point in time instantiate that cohort and work with that. Or, I mean, at this point, when this thing is finished, you have all the data that you need in this cohort method data object sitting in R. So that is also a constant thing that you can later come back to. And that's also why I made this an atomic thing. You get all of the data in one go, and then afterwards you never have to go back to the database again, just to also make sure that you don't run out of sync with versions that you got one bit of data and the other bit of data. So.
Yeah, and specifically given the situation you're describing, I would certainly advocate for, at that point, grab the data once for that one moment and work in R after that. Don't try to keep your database in sync. That would be a nightmare.
But you do pretty big studies, right? I mean, you run out of RAM, you run out of bandwidth, you run out of database connections.
Nope. So this object is using the FF package, which is basically, it uses memory mapping. So it basically stores the data object on disk, but it's accessible as if it's in memory. So we run this on very large databases, on very large populations with large number of covariates, and like the files that get written to disks are sometimes like hundreds of gigabytes, but that's fine. It's just a bit slower, but it's fine. And like we have nifty database servers, so it actually is also pretty quick to get it from the database. But it is designed to run on very large problems.
I mean, it's all been tested to work on the standard environment, so you don't need to have something fancy to do it. It just might be slower, is basically what it comes down to. So throwing more hardware at it will make a better solution, but if whatever existing hardware, this won't break, it just might be slow.
Yep, that's right. Also, because this is like a special type of R object, you can't just save it with the usual save function in R. You need to call this function save cohort method data, because it needs to copy those FF objects to a specific folder. All right, so sorry.
So I'm just curious, is it common practice for reproducibility's sake to document the day that the first person runs the study and then everyone kind of truncate their data from that? I understand for a really long study, maybe it doesn't matter, but if the drug was released in 2010 and there's a flu outbreak in October or something, do people do this?
So to be honest, we never had a problem that the database that we're running off of is non-static. But you should definitely document when you run the study and on which version of the database. Usually we do that because the name of this schema actually contains the version number, but yeah, in your situation, you should definitely record when you run it. And one thing to do is that actually I want to add a lot of logging. So that on the fly, it will create a log, timestamp log of when something was done. So that should automate that bit. But for now, you should record it.
Is this function executing queries in parallel or just one query at a time?
One query at a time.
Is the save cohort metadata basically save individual level patient by patient and all their covariates into a sparse table?
Yes, exactly. So the question is it storing all of this data at a per person level in a sparse matrix? So these covariates are indeed stored per person in a covariate.
So in order to use this package, you have to link it to your database. So this package is going to just do a data analysis, or is it going to write some data to the database itself?
So the way that we use it now, it's not going to actually send data back to the database. So it needs to be sitting on a computer that has a way to connect to the database. Yeah, it doesn't have to be. So the server usually is somewhere else, not on the same computer. Like you could be working on your laptop, but it needs to have a network connection and a logical path to the server. Go ahead.
The target IDs, comparator IDs, those are just used to go to remote database and fetch the definition of that cohort, right? It's not bringing the data of that cohort from the data.
It's bringing the data of those cohorts.
So it's bringing the data and then putting that data directly into the save into the R server. So R server doesn't go back to its own database to get it. It's just using the Atlas database where the Atlas can hosted that database to get the actual CDMs.
Yes. So after this function is done, you don't need to talk to the database anymore. Everything is in R. All the data is in R that you need to find out.
Because that question about the code and in this scenario, if you are using the Atlas database, it will be an Atlas database. I would say you are not writing anything.
That's right. All right, but let's continue because I think people are getting anxious for lunch. All right, so very quickly, once we have this object, we may want to call the generic summary function on it just to see what came over. So if we do that, we see that we got information for these T's, C's, and O's. We see that there are about 19,000 people in the target group. 51,000 people in the comparator group. We see that. So what I failed to mention was that the outcome cohort is actually already subsetted to the people that are either in T or in C. So we now have 8,000 people that are in either T or C that have the outcome. It's not saying whether they had it before or after the index date, because that's something we will work on later. And we also see that 827 covariates were constructed. And there were 2.4 million non-zero values for those 827 covariates across the T's and the C's.
When you say treatment concept ID and person IDs, or is that?
So these are the Atlas IDs for the, or in CDM speak, it's the cohort definition ID. Field in the cohort table. Oh.
So the number of treated persons are individual persons, unique persons.
Yes, that's the number of individual persons. Yes. All right, so that was step one, getting all of the data. Step two, once we have the data, we can use the data to define our study population. And most important, well, so one aspect of what we call the study population is, do we want to remove people that had the outcome prior to the index date? And so in this case, we say yes, because I think that's what Graham also did. Another choice that we need to do is we need to define the time at risk. And a time at risk has a beginning and an end. And that may or may not be exactly the same as the cohort start and cohort end date as Patrick defined, and Atlas defined. And so we can define the cohort, the time at risk start and end relative to the cohort start and end using these 4 options, if you will. So we're saying that risk window start is 1. That means that it's the cohort start date plus 1, because that's actually what Graham said. Follow up again on the day after first qualifying anticoagulation prescription fill. So we're just doing exactly what Graham said. I have this option, add exposure days to start to false, which means that this 1 is relative to the start date that Patrick defined. We said the risk window to end, but I've said add exposure days to end to true, which means that the 0 is relative to the end date that Patrick defined, the end of exposure as Patrick defined it. So basically what I'm saying is here is the time at risk starts on 1 day after starting the cohort, which was defined as initiating the treatment, and it ends at the end of the cohort, which Patrick defined as being the end of the exposure, or at least until there is a 3-day gap in exposure. Is that clear? So why didn't I specify this already when I was getting the data? Well, the reason for that is simple, is that maybe we want to do some sensitivity analysis and play with this, and we don't want to be talking to the database all the time. We just get the data once, and then we can create 2 study populations where we may have different choices for the time at risk window, for example. So it's an efficiency thing. All right, now we need to create a propensity model. And that's actually, in general, pretty easy. I call this function createPS, and I give it the CohortMethod data object that I created in step 1. I feed it the study population object that I created in step 2. And you can just leave it like that, and it will use the default settings and fit the propensity model. So what are the default settings? That is a lasso logistic regression. You can choose to use something different. You need to look at the manual and see what the options are for this thing. But I mean, we tend to use that because it gives pretty good results. Again, it's nice to just put this up here, but this could take a long time. If you have 50,000 covariates in a very large T and C, this could again take like 6 hours or something easily to complete. Well, so this is no longer on your server. This is done on your computer, maybe your laptop. So it could actually take 6 hours on your laptop. So this is not yet matching. This is just creating the propensity score. So the propensity score is just the prediction for each person whether they were going to get T or C. Yeah.
I think I wouldn't get hung up on compute when Martijn's talking about that. That's basically if you have a massive data set and a massive cohort and a massive number of covariates, then it's going to take a lot of time to do. Many of you who are doing small cohorts with small number of variables, like we've run some of these cohort methods using the exact same package, and it takes like sub-minute to perform an analysis. What he's warning you about is like if you do the biggest study imaginable, don't expect it to be done sub-second.
Yeah. Showing your penchant and expertise for comparing methods, the default settings that will run on this, is that a result of a comparison of different versions of constructing the penchant score?
Yeah, it is. Although that particular evaluation, we don't have that published anywhere. But
Yushi!
Yes. Well, Yushi is writing a paper specifically on why L1 regularized regression is a good option here, at least compared to something like.
I remember Yoshi's description of that presentation, so that's great. I just wanted to make sure that's there to rely on when we're writing up how that was done. Look forward to being able to reference.
Yeah, hopefully in the near future we can reference.
Is this to
absolutely right. So because the L1 regularized regression needs a hyperparameter on how much regularization to use, it uses by default 10-fold cross-validation with 10 replications actually per fold to get to the right hyperparameter.
And is it just do it one time? So it's not like, for example, if like you have to figure out C.
Yeah, so that's why there are the 10 replications. So it's doing it 10 times. That's the default settings. Yes. That is maybe a little bit extreme, but we use this package quite a lot in our internal studies, and we have found that it can be a little bit, the results can actually be sensitive to how well you pick this hyperparameter. So it's better to just throw more computing power at it and get it right.
Is there a framework built in for evaluating the robustness to all of these kinds of choices? Or some of these choices, is that in terms of actual?
So we are doing a lot of evaluation research that is evaluating all of these options. But what you could also do in your study is just have sensitivity analysis and try different options and see how that changes your estimates. And it's actually fairly easy to do that with this package, and the abstraction layer that I'll be mentioning in the afternoon helps doing a lot of these different analyses very efficiently.
Yes, to put everyone in the room at ease, you can handpick your 20 favorite covariates and do a standard logistic regression just as easy as what Martijn is describing here.
Yes.
Everyone feel better?
We don't recommend
Now don't do it.
Don't do it. All right, so now that we have a propensity score, we may want to look at the propensity score distribution. We're not, well, you can do it, but we actually typically show a preference score distribution. So what is the preference score distribution? It's just a simple transformation of the propensity score, taking into account the different sizes of the two cohorts. Because sometimes when one cohort is much bigger than the other, these plots, if you just show the propensity score distributions, are all skewed all the way to one side or all skewed all the way to the other side, and it's really hard to read those plots. So we do a very simple transformation. It's actually, there's a paper describing that it's a good idea, so you can actually reference that. It just makes for nicer plots to interpret. And so that means that a preference score of 0.5 is that given the prior probability of receiving one treatment over the other, it actually is actually not making a difference, apparently. So on the x-axis is the preference score. The blue distribution is for, in this case, warfarin. The red is for the bigotrin. So what is this plot telling us? Any guesses? What can we learn from this plot? Yeah, there's quite a lot of overlap. They're pretty similar. Most of them are in the middle and actually overlapping. So it's not necessarily saying that these cohorts are comparable. It's only saying that based on the covariates that we had, it seems like they're actually pretty close. So that's a good thing. That means that we can continue with our study.
What does it look like if we were to use all of the covariates, though, Martijn?
We'll get back to that later.
What the rest of the class wants to do.
All right, so now we come to matching. And so we can just say match on PS, another function, feed it this propensity score object that we just created. We set a max ratio of 1. So we also support what's called variable ratio matching. So in this case, we're doing one-on-one matching, meaning for every person in the target cohort, we pick one person in the comparator cohort that has a similar propensity score. But we could increase that max ratio to, say, 100, and then it would just keep on trying to find other people in the comparator cohort that also have similar propensity scores.
So this one-on-one matching, do you randomly pick one that match your target cohort, or pick the one that most closely match?
Yeah, so it's, to answer your question, it's greedy matching. So we start by computing all of the, let's say, differences between everybody in the target group and the comparator group, and then it starts by what is the smallest difference that I've observed. And so that's the first match I'm going to make. And then we go, oh, what's the next smallest match? And it just keeps on going. One one thing we use is what we always specify is what's called a caliper, which is basically a limit on how far what is the biggest difference that we allow people to still be matched. So Graham actually didn't mention whether they use the caliper, but you should really always use the caliper. You just don't want this to run out of control. In this case, we specify the caliper to be 0.25 on a standardized scale, so basically 0.25 standard deviations of the propensity scores, the maximum allowed distance.
So if you cannot find a good match within this 0.25 category, then this person is strong.
That's right. So if you don't use a caliper, you're guaranteed to, well, almost guaranteed to have all people in the target group, unless there are less people in the comparator group. But if you do use a caliper, you might actually lose people in your target cohort because there's nobody within the caliper that matches that person.
One of the things that when I was looking at the paper I was impressed by was how well balanced the two groups were across a large number of covariates, even though, like, from what I see here, this matching is based on propensity score, and basically the distance metric is propensity score. There's nothing is there something within the matching process that's actually forcing the balance across those things in the propensity score? Because to me, it was actually shocking to see, like, they were within one or two, unitary units.
That is a very interesting point, that balancing on a single variable seems to achieve this balance on all of those other variables. It's not guaranteed to be, and Christophe actually has a nice paper and a package on how to take that further and actually maybe balance on all of these covariates in a way that's actually guaranteed to have these balances.
It was a nice lucky strike. There was nothing in the matching that actually
trained you to do that. There is also just the fact that those covariates are actually going into the propensity model, and therefore there is the expectancy is that you will balance on them, but it's not guaranteed. And I'll actually show you the balance a little bit later on. Another thing to look at now that we've done our matching is, well, how many people are left after our matching? So we start off with our original cohort, and that's actually, those are the cohorts as defined in Atlas. And so there are already a lot of inclusion and exclusion criteria that Patrick showed that went into choosing these people just to get to these numbers. But of course, the cohort method package doesn't know at all about those criteria. It just knows what was in the cohort eventually after all of those criteria were applied. But then they came into the package. We removed people that had a prior outcome, so we see how many were kicked out. We required them to have at least 1 day at risk, and I think somebody raised the point, well, maybe we should increase that number. Let's say they should at least have 30 days at risk. We could do that if we wanted to. I don't think Graham did. And we matched on propensity score, and we lost quite a lot of people. So we lost 306 people that apparently didn't have a match within the caliper in the target group. And we lost a lot of people in the comparator group because we did one-on-one matching, and that means that because our target group is only 90,000, we can only at most pick, well, in this case, we had 17,000 people in each group. This is an argument why you probably want to use variable ratio in matching instead, because then you can keep those people in, most likely. But that's not what Graham did, so we use one-on-one matching. Oh, and these last numbers, these are the actual numbers that go into the Cox regression.
Is there evidence of variable matching will be better than one-on-one matching when you have the option to choose? What do you recommend?
So I recommend variable ratio matching in general. There are some papers that show that you keep more power and are still accurate. It's just those papers, I don't like the way that they evaluate that, because they usually use one study as an example and show in this study the point estimate moved in this direction, which clearly was the right direction for it to move. And so we say that it's a good idea to do variable ratio matching. So we're actually doing a very large scale evaluation. I had a poster about that yesterday where we actually are doing a much more systematic evaluation of whether it really is a good idea. And so hopefully that will tell us whether one-on-one ratio one-on-one matching is worse than variable ratio matching. So hopefully in a few weeks I will be able to give you more.
So the variable matching, there cap how much the ratio will go up?
Well, so I usually just set it to 100, which basically means just keep on going. So the way that it works internally is it first does the same thing as the one-on-one matching. So for every one in the target group, it tries to find one person in the comparator group. And then after that is complete, it will go to another round. And then of the people that are left, we'll try and see if it can add more. And then we'll go back. So at least everybody should have at least one good match. And then you'll keep on adding within, of course, the caliper until you run out of people or run out of people that are within the caliper. So a point also brought up, well, what about covariate balance? So we have a function to compute covariate balance, and we can call another function to plot covariate balance. And so what this function is showing is on the x-axis. I need to say what is covariate balance. It's defined as this. We usually use standardized difference of mean, which basically just is if you have a binary covariate, you just take the proportion in the target group, the proportion in the comparator group, and take the difference and divide that by the standard deviation. And a rule of thumb is a standardized difference of 0.1 or smaller is acceptable. And don't ask me why, but that is what people do. And so this plot is showing you every blue dot is a covariate that went into the model. So we had 827. On the x-axis, it's showing the difference, standardized difference before matching, and on the y-axis after matching. And so what you see is before matching, there were actually some variables that were out of whack or unbalanced. It would actually be interesting to know which ones those are. But after matching, you see that those have gone away. So even though we had a nice overlap in propensity score distribution, there were some variables that were actually unbalanced before the matching. But after matching, we're very happy because it's a very low difference.
I guess in each study's Shiny app, which is sort of the vision to come, is that they'll be dynamic and you can pick out instantly what each of those variables are.
Yep. Oh yeah, Graham also said that they said, hey, standardized mean difference of smaller than 0.1 indicates a negligible difference. So they also use the same rule of thumb that we usually do. All right, so the last step, once we've done our matching, is fitting the outcome model. So we have a function, unsurprisingly, called fit outcome model. We input the matched population. We specify that we use a Cox model. One thing that's unclear in the Graham paper, so very often when you do one-on-one matching, what you effectively do is you create matched sets. So you match one person in the one cohort with one other person in the other cohort, and that is a matched set. And then the question is, if you do a regression afterwards, do you condition that regression on the matched set or not? And so Graham didn't say what they did, and so I just set that to false, but I could set that to true as well. It might cost you some power, but it protects you against residual bias. So we have an option of actually including all of the covariates that went into the propensity model also in the outcome model, but that's not what Graham did, so we're also not going to do that.
Why is the use covariates set to false?
So in this case, we're doing a Cox regression. So normally what people do is the only thing that go into the Cox regression is the matched population, and as basically the predictive variable is the treatment. That is the vanilla way to do this. But you could also add other variables into that Cox regression. And so you could, the same 825 things that went into the propensity model, you could also use those same variables in your Cox regression and basically compute betas or coefficients for each and every one of those to do what we call a doubly robust estimation, which is basically adjusting for the same variables twice. And so you could do that. The reason why I'm usually not very happy about that is those 820 covariates is nice and easy to fit when you're trying to predict treatment, because we have 20,000 people in the one group and 40,000 people in the other group. So it's easy to fit a model that has 825 or even bigger if that's your sample size. Over here, we have maybe 100 people that have the outcome, or maybe even less. So you're trying to fit 825 variables on 100 people. So I'm usually not a big fan of including covariates in the outcome model. But in theory, you could. And that, in theory, should make you more robust to model misspecification. But if you don't have enough power.
Yeah, on the note of model misspecification, the hazard ratio is not a collapsible measure. So you actually have different interpretations for the two models. If you include the covariates or don't.
Well, that's why they
Is that you talk about the literature at all? I mean, I don't know. In this literature?
Not that I'm aware of, but that doesn't mean that it's not discussed.
Well, mathematically it should be. I think Sandra Greenland pointed it out. You have the genealogy literature. Is there any sort of discussion on the forums about that feature of the model outcomes?
No, because we usually, like I said, we usually do not even have enough data to actually fit those models properly.
Have enough events in each of the sub-cells that you would have.
Quite often when you're at this point in the analysis, what you're left with is single-digit numbers in each of the cohorts that have the outcome. So what are you going to do?
And you guys have not built in any sort of like way to throw a flag if there are too few events in each sub-cell when you include all 825 covariates?
Yeah, it will throw an error and say there are too few people in these cells.
Okay,
yeah.
great. Thanks.
Is there a way to specify an interesting set of covariates, perhaps to review something, certain risk factors, other modifiers, just put in a subset of alternatively stepwise regression approach in the screen for?
So yes, you can define a subset. In theory, you could do a stepwise approach, but stepwise that's a little bit dangerous, of course, if you're doing so many multiple tests. But if you wanted to do a subset, there are parameters or arguments to this function that I'm not showing here that allows you to just
define set of covariates.
Yep. All right. Inspecting the outcome model that came out of it. So again, just calling the summary on this outcome model object will tell you that we fitted a Cox model without stratification. And it will tell you what the estimate is and the confidence interval, 95% confidence interval. It will also tell you some more information, like how many people were there in the two different groups that had the outcome. And we see that actually there are 164 in the Bickerton group and 155 in the comparator group, which is a little bit odd if you think about the hazard ratio being smaller than 1, but it's actually not because the number of days in the two groups is different as well. So people were longer in the Bickerton group than they were in the Warfarin group. So if you compute the incidence rates in those two groups, you actually see that the incidence rate in the Bickerton group is lower than in the Warfarin group. And that by itself already explains why you have a hazard ratio smaller than 1. If you compare to what Graham found, it's actually very similar. So they found 11.3, we found 12.2 here, 13.9, 40.3, and they have 0.8 and much narrower confidence interval. We have 0.9, but we apparently had less power. So their confidence interval is almost completely subsumed in ours. So we're actually pretty good at reading. I think we use the Medicare. Yeah. Yeah, the Truven Medicare supplementary beneficiary databases. So those are people on Medicare that had supplementary coverage. All right, we can also create a Kaplan Meier plot by using the plot Kaplan Meier function. I provided labels just because I thought that would be neat. And by default, what we do is we do include basically confidence intervals on these things. We not only give the number of people in each group. And so here you see that even though there is differences, visual differences between the two lines, most of that is explained by random noise.
So just to repeat, you use the same data set. You try to replicate as well as possible.
Not the same data
Not the
set.
same data.
Oh, not the same data.
No.
It's a Medicare population, but it's a people who have supplemental insurance as opposed to the broader.
So in theory, it should look exactly the same if it were on the same population.
We've replicated the study, not the data.
Yeah. Well, and we had to make some assumptions here and there, so it's very surprised that we got exactly the same result.
We were not expecting that close.
All right, so this is what our Kaplan Meier plot looks like, and so this is what theirs look like. So because they don't have the confidence intervals, I think it's a little bit misleading in suggesting that there's a large difference. So to recap, the steps taken is step 1 is getting all the data from the server into R. 2 is defining the study population. 3 is creating a propensity model. 4 is matching or trimming and matching, stratification or whatnot, using the propensity score. And 5 is fitting the outcome model. And of course, during that whole process, generating statistics like the covariate balance plots and the propensity score distribution plots. So just a quick segue, and then I promise we go to lunch. So we usually don't handpick covariates. So what would it look like? Reason is you might miss an important confounder. You might actually not know what an important confounder is because it might not be exactly what you thought should be included but a proxy, but that's still good. And it's rather subjective. So somebody else will pick different covariates include, so it's a non-reproducible way of doing a study. So we just throw in all predefined covariates and use the regularization to decide which ones end up in the model. Just to show you, and the bonus, of course, is that's more work for the computer, less for you. So how would you do that in the package? So if you create your covariate settings, just turn everything to true. Although these interactions with month and year, we usually set them to false, but they're actually going to disappear soon. However, you do need to do one additional thing, because here we are creating covariates for everything, including all drugs, and then including drugs that are initiated on index date. And that means it also is going to include the bicatrin and warfarin initiation on index date, and that's going to make the whole thing perfectly predictable, because that is the definition of treatment. So you need to explicitly exclude those concepts and all their descendants. So that is the caveat that when you do that, you need to do that pretty, you have to think about it. If you don't, actually, when you fit the propensity model, it will throw a warning or an error saying, this is perfectly predictable. You probably want to exclude these covariates. Because, of course, we made that mistake ourselves quite often. So what does that do with the propensity score distribution? So this is using Graham's covariates, and this is using everything. And that actually looks a little bit different in that there is this subgroup of warfarin users that apparently are different when you look at all covariates and not just the one they picked. I'm blanking on what those are, but so that is actually interesting to know, right? That they appear to be different. So if we do the matching, we see that this actually ends up in fewer people that are being matched. So we are throwing away more people. We're throwing away people that are not comparable to this new subgroup, basically, of the bicatrin warfarin users that we identified. So we have fewer people. And the question is, what we also see, if we look at covariate balance, so these are just the 825 that Graham used, and really good balance after matching. And these are the 50,000 that we used. And you see actually that we also achieve really good balance with all of these 50,000 covariates. So that's actually pretty awesome, because that means that in any sense that we can extract from the data, they now appear to be balanced, including the 825 that Graham uses. It's a better guarantee that they're actually comparable after matching. So did this have any effect on the final estimate? Well, so before it was 0.9, and after the hazard ratio is 0.95. The confidence interval, of course, got wider because we had fewer people, and in the end, it actually didn't make a very large difference on the estimate. Could have, but in this case, it didn't really have a big impact. You do see, if you look at the Kaplan Meier plot, that these first, 150 days or something here, there was still a difference between the two groups, and that actually now is completely gone away. So it does, maybe if you look very closely, have a bit of a difference on the effect.
It is published now, the work with Rachel, I forget where we got published. We have a paper where we showed that it has a very big effect.
Yeah, so we actually just published another paper on a different topic where actually we show that this makes a huge effect. And I think this is ibuprofen compared
drug
to
safety? I don't remember where it's published.
I don't remember. But that is, so most people do not include, of course, all covariates, and they get to like a really large effect, and there's large agreement on this really large effect, and we show, well, if you throw in all covariates, then this effect, well, at least, we didn't show the effect yet, but at least
I'll find the reference and send it to all you guys.
It can have a big effect, and that's why we prefer to always use all covariates, also because it's easier and we're lazy. All right, so in conclusion, we can use the OHDSI tools to replicate the gradient study. We actually got almost perfect agreement on the effect size. But the diagnostics are an important part of both design and execution. And they show actually the impact of adjustment. So we saw that before matching, there was actually a couple of covariates that were out of balance, and we were able to correct for that. We also saw that there was a lot of attrition. We lost quite a few people by the matching. And then one question that I think was already came up earlier is, well, what does that do to the generalizability of our results? Because now we have a finding, but it is only relevant, or it only applies to the people that ended up all the way in at the end of our analysis, which is not the same group that we started with. So does that generalize? I don't know. Maybe there's a different effect in that overall population. So that is something to think about. And so we do not recommend handpicking covariates, but it is supported by the package.
I was going to say it's just a tremendous contribution to the community. Thank you and Marc and everybody who contributed to so much. And I remember a few months ago, you guys were talking about unit testing. There was a call for people to contribute to the effort to do unit testing. And since you're speaking to a whole group of people who are now going to be starting to use this package all the time, is there a route to follow for people who want to contribute to that effort? I know there's good coverage as it is, but I mean,
really are keeping people from lunch here, so this is dangerous. But so an important question when you have tools like this is what is the validity? How well is all of this programmed? And if I specify a certain time at risk, does it really work out the way that I specified it? And so to make sure that that is the case, we have several approaches to verifying the validity. And one that we especially rely on is unit testing. And what is a unit test? It's this very small piece of program that tests a bit of functionality. And so we use a lot of large-scale regressions, and you want to know that those regressions actually end up producing the right results. And so we have, for every type of regressions, we have several unit tests that actually test the result that come out of it and compare it to known results to make sure that all of this is doing what it should do. But there are a lot of things that are not yet covered by unit tests. A lot of things are. And so if people want to contribute and get to know the packages better, we always invite people to write unit tests. Just to whatever piece of the functionality that you think, I want to make sure that that is actually happening the way it's supposed to happen. You can write a small bit of R, test whether it actually passes, and you can give it to us, and we can include it in the package. And every time a new version is released of the package, that bit of code is run automatically to make sure that it still passes the test that you have. So every time we release a package, it runs all the unit tests, and we're at least sure that it passes those tests.